So we move on from double integrals in Cartesian coordinates to talk a little bit about polar coordinates. Why would we do them in polar coordinates? Well, so far, a lot of the regions we've had are either, nice Cartesian things like rectangles, triangles, maybe the occasional thing where we've got some, y equals f of x or whatever. But what about regions that are, like annular or circular or Pac-Man-y? These are regions that are best done in polar coordinates. So we better figure out how to do them in polar coordinates. So we recall, of course, our good old-fashioned conversions, right? X equals r cosine theta and y equals r sine theta. It also behooves us to keep in mind, right, that x squared plus y squared gives us r squared. And so we can easily convert functions from x and y into r and theta. The question is, how do we convert a whole double integral? How do we do a double integral in polar coordinates? And the secret is that we take our region and we carve it up, but instead of carving it up into squares dx dy, we carve it up into regions that have a certain angular extent delta theta and a certain radial extent delta r. So let's take this block here just as an example, and we want to ask, what is delta A? What is the amount of area that's in that little block? Well, one of the peculiar things about polar coordinates is that these blocks are no longer of constant size. Actually, as you go further out in R, the blocks get bigger. So if we look at this little block, it does kind of look like a rectangle though, and using some calculus magic, we can kind of squint and assume it is a rectangle. And it's got a length on one side of delta r. And on the other side, so here's our delta r side, and on the other side, we can ask ourselves, what is that? If you recall back to the definition of the radian and of arc length, that other side is actually going to be r delta theta. It's going to be r delta theta because the arc length, if you take a certain part of a circle, right? If you take a little wedge of angular extent delta theta and it goes out r, this side is actually r delta theta. So we end up with this delta r times r delta theta, or if we're writing it in differential form dA, it's r dr d theta. So this is, again, really interesting. The size of our little brick dA, our little tile dA, changes with radius. So what do we have to do in order to do a double integral in polar coordinates? Well, we're going to start by saying, well, what if we start with f of xy dA? And what we're going to do is we're going to convert this into polar coordinates. So the first thing we need to do is convert f into polar, into r and theta. The next thing we're going to do is our dA, we got to write our dA. So the second most important step is, don't you forget r d theta. You need to have that extra r in there. You need that extra r in there no matter what else you're doing, because if you don't have that extra r in there, this extra r is what I mean. You need this extra r in there. That's the cost of doing business in polar coordinates. So it's really, 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 really important that you do that. And then if you've done both of those things, then you get to set up your bounds and evaluate them. In polar. So I do want to take a moment and I want to look at an example of why we might do something like this in polar. So let's say that we want to integrate a very simple function. We're going to integrate f of xy equals x. Carve off a little bit of room here for ourselves to do this example. But the region that we want to do it over is one petal we're going to integrate over the first petal of r equals cosine of 2 theta. Just one petal of r equals cosine 2 theta. Actually, we're going to do something a little bit different. I apologize. We are, in fact, just going to find the area of this. Getting a little ahead of myself. We're actually just going to find the area of this little petal. Well, what we got to do is follow our instructions, right? So let's go ahead and set this up. If we're finding the area, we recall that the way we find our area is through the double integral of 1 times dA. So in this case, this is going to be the double integral in polar of 1 times r dr d theta. Don't forget that extra r. You always need that extra r. Now in this case, we got to set our bounds. R goes from 0 out to cosine 2 theta. R goes from 0 out to cosine 2 theta. And then we have to figure out what our bounds on theta are. Now there's a couple ways to figure this out. One way is to kind of look at this lobe and observe that it kind of gets nice and tangential here. You can also plug in values of theta and figure out when it comes back to the origin. But this does, in fact, turn out to be from negative pi over 4 to pi over 4. And that's how we're going to find the area of this little loop. If we actually evaluate that, it evaluates like any other integral. This becomes 1/2 r squared, or in this case, 1/2 cosine squared 2 theta. And again, you might remember from BC Calculus, right, that they taught you how to do this in BC Calculus as the integral of 1/2 r squared d theta. Well, you were always secretly doing a double integral. Cosine squared, by the way, is a funny one. We're actually going to end up doing a lot of cosine squared and sine squared integrals this year. So this is an identity that you're going to need quite a lot. Cosine squared of x is also 1 plus cosine 2x all over 2. So in this case, I'm going to grab this 1/2 and this 1/2, and I'm going to rewrite this. I'm going to pull them outside. I'm going to rewrite this as 1/4 negative pi over 4 to pi over 4. 1 plus cosine 4 theta d theta. Why is it 4 theta? Well, we've got 2 theta here and here in our identity. So this ends up being 1/4 of theta plus 1/4 sine 4 theta from negative pi over 4 to pi over 4. And I just want to point out the sine term here is actually going to do nothing. Because when I plug in pi over 4, I get sine of 4 times that. Sine of pi, which is 0, and sine of negative pi, which is also 0. So I don't get anything from that term. So all I get is 1/4 of pi over 4 minus negative pi over 4, which is, of course, pi over 2. 1/4 of that. The area of this region is pi over 8. And that is an example of how we will do double integrals in polar coordinates.